he does not cover this well. But I want to tell you, this is very important. And it is it's going to use some signals and system stuff more so than just macro equations. Matter of fact, it's also going to some systems. So we're talking about bandwidth. Now, Wentworth's his whole thing with EMC is geared towards real electromagnetic compatibility. He talks about what wires look like, what inductors, capacitors, and resistors look like. But all that stuff's meaningless unless you know what the signal looks like. And because right now everything is digital. You have a rise time, a hold time, and a fall time, and then the thing repeats itself. Now, y'all had your digital technology courses, right?
Yes, sir.
I mean, you had something where, you know, there's non-return to zero, return to zero, there's plus minus one. There's all sorts of ways of signaling. Generally speaking, when we send information, digital information, through a cable or something, all that stuff is going to use frequency modulation on a carrier frequency at a certain very high frequency. Y'all follow me? Then it's extracted. So at least appreciating that. When it's extracted, and you get down to what we term in radar baseband, it means the raw digital signal, where it's going to have a rise time, a hold time, and a fall time. Now from that, you can turn it into non-return to zero. You can turn it into anything. But for now, it's going to have a ramp up, a hold time, and a fall. Here's what the actual signal will look like in the spectral domain. I tried to do this on Friday. I didn't finish it. Y'all with me on this? Do you remember Friday's lecture? Mm-hmm. All right. So in general, you don't have to write this down. I'll tell you where you need to write, because this is what we did on Friday. I started out and I said if I had a digital waveform, where it had a rise time, it stayed on, fall time, and then it repeated itself. This is going to be in the time domain. I talked about this being a rise time, right? And then from the 50% on, 50% off, this is actually tau. That's the on time. And this is standard digital notation. Then there's going to be a fall time. Normally we take T fall equal to T rise. We take whatever is shorter and we use it. We don't care if they're one slightly different. We don't. And then there's the time over which it repeats itself, which is called T, and sometimes in radar we call it the pulse repetition interval. So that's from last time. Now I said because it is a periodic signal, you might as well give this height A here. I can represent it in terms of a Fourier series. Now, one thing about engineering, when I was where you are, I wish somebody had told me this when I was taking just a pure math course and series analysis. I didn't see why you had to take a perfectly easy to understand function and turn it into an infinite series. But I do now, and I did as soon as I got into double E, because the frequency spectrum is revealed by the coefficients of the Fourier series, okay? This is critical. So I'm going to say that x of t here can be given as a summation, right, of c of n e to the j n omega naught t, where n goes from minus infinity to infinity, and we know that omega naught is really 2 pi over the period t, and we can also say that c of n is equal to 1 over t, the integral from minus t over 2 to t over 2 of x of t times e to the minus j n omega naught t dt. If you want to see the proof for this, I'll be happy to do it after class. All right, this is a standard. You're going to see this probably all the days of your engineering career, unless you're in marketing or just in fabrication of micro devices or something. But this is used for everything. You have to have this understanding. So we could do this. We could put in x of t here and do the cold cut. We could just do this integration, right? I showed you the trick. And remember this. Do you remember what I said to do? How many do? Yeah? You said it. What I did is took the derivatives twice, right? Do you remember the reason I did that?
Impulse.
Well, what happens is every time you take, if you look at this equation right here, when I take a derivative, take a look now of this equation right here. That c of n value is not a function of t. Y'all see that? Please take a look. Y'all with me on this? So if I take a derivative of this with respect to t, the thing that happens is a j n omega naught comes out in front, right? Take a derivative of e to the j n omega naught t with respect to t, the j n omega naught comes out, right? If I took a second derivative, then this would be squared. As a matter of fact, if I took an nth derivative, the j n omega naught would be to the nth power. Are you with me? I want you to follow my reasoning on this. This is important. It's very valuable, very useful too. Everybody with me on this? Now you're going to say, well, so what? Well, that second derivative of x with respect to t squared, you can view that as just a new function. Call it y of t. Right? A double derivative of a continuous time function is still a function, and it is periodic. Do you all agree? Right? So because of that, I can say this thing also can be represented with a new Fourier series. Call it C, maybe not C, let me call it AN e to the JN omega naught t, right? Where n goes from minus infinity to infinity, and here AN, like CN, because it's periodic, we went over the period, the double derivative, and now it would be the second derivative of x with respect to t squared integrated from minus t over 2 to t over 2 times e to the minus jn omega naught t dt. Are you with me? And this is the a of n that goes there. Now, what is that a of n? Well, and this is the coupler, so put this down here. My a of n there, right? If I divide that by jn omega naught squared, I get my c of n. Or I get the coefficient I wanted. I get this coefficient. Do y'all see that? Because I want the coefficient c of n that's of the x of t series, right? Making sense? How many understand what I'm getting at? Do you understand, Jake, or not?
I understand what you're doing, not necessarily why you're doing it.
Well, the reason is I need c of n, and this is a lot easier because if I take two derivatives of that, I just get impulse functions. And evaluating the c of n double prime, or this, I call it a of n, but it's really a double prime c of n, is easy. As a matter of fact, if you remember from last time, how many remember me doing derivatives last time? Right? When I take two derivatives of that with respect to t, what do I end up getting? This would be x double prime of t. Do you remember? Well, here I'm going to get the first derivative is just a constant a, right? Between 0 and t rise. Then it goes to 0. Then it's a minus a from t rise to t rise plus tau, right? Then I take another derivative and now I get impulses. And the height of those impulses are going to be what? Matter of fact, why don't we just do this? I'll take the first derivative so you can see. Let me do it right under that one, just to make sure. I'm going to try to keep this, you all understand what I'm doing here. So the first derivative would be what? X prime of t would just be this, right? It would be a constant, goes to 0, then another constant, this is going to be versus time, it would repeat itself, right? This height would be a, right? And, excuse me, a over tau, tau rise. And this height would be minus a over tau rise. Y'all agree with that? Nathaniel, are you with me? That's first derivative. Second derivative is going to be what? Well, this is my point last time. When I take a second derivative, now, when I get this, I go from 0 to a tau rise over tau rise, right? In an instant. That's an impulse function. Y'all with me? Take a derivative of something that has a discontinuity, you get an impulse, and the front end, or the coefficient, or the weight on that impulse is just the magnitude. So it goes up, and it's simply a over tau rise. The way we always indicate impulses is just an arrow. You probably remember this, right? Simply an arrow like that. Then here I get an impulse too, but Jack, what's the value?
Negative a over 2.
Right, it's minus a over tau rise. Keep going. Here what happens?
Shoots up to a, or
It goes down.
Still down, yeah. Goes down to minus A over tau rise, and then finally, here it does what? Shoots up to A over tau rise, right? And you can see the progression, right? Are you with me? Are you okay with what I did, or you got a question? Okay, I want to make sure. If you have a question, now's the time to ask. I'll try to clarify. I'm just going through the process of what I did Friday. Now this waveform right here is what we're going to get the coefficient for. And you remember one thing, that anytime I had the integral of delta of t minus any constant times any functional form of t dt, if I integrate that from minus, it could be really over a much more limited interval. But what actually happens? Is this going to have any value but 0 when that delta function is not turned on? It's 0, right? The only time things change is when the delta function goes from 0 to infinity, it has an area of 1, and you simply find out, you simply evaluate whatever its time multiplying at that point that the delta function does its thing. With me? This is a very simple delta function. I'm not trying to make this complicated. So when I do this and get the coefficients here, that's the reason. And I'll do it here. You're going to have to believe me and thank me, some of you, for doing this. So if I take and I look now at C of n double prime, really, I got 1 over t, the integral from, I call it minus t over 2 to t over 2. When you do these integrations to evaluate the coefficients, it has to be over one period, but it can be over any length of time that covers a period. So I always pick a time that's conducive to not having transitional points. So I take it from down here to here. I know I get the waveform, but I don't have endpoints that are where there's a discontinuity. You with me on this? Remember that. So if I do this, well, the first, I know I'm going to have what? A over tau rise is my way. The first delta function occurs at t equals 0, right? Second delta function occurs at t minus tau rise, right? Third delta function, and this is going to be tau. Now the reason is because tau is measured from the 50% point here and here. If you slide that back, you see this point right here is tau. You all agree with me? Finally, what happens? The last one is what? J. What happens to it? Is it negative or positive? Just look up here. The last delta function is
Positive.
and has the same weight, right? So, in what time does it occur? T minus the quantity tau plus tau rise. Right, now I have to add the two taus, don't I? I have to take, because now it's going to be tau rise plus the width tau, isn't it, class? With me? And then finally I have to multiply this stuff times e to the minus j n omega naught t dt. But here's the beauty. This whole mess right here are delta functions. As I integrate, the only thing I do is evaluate this exponential when they turn on. That's it. And multiply by the weight, which is a over tau rise divided by capital T. Whenever you hear the term weight used by an engineering professor or a math professor, it's the coefficient next to whatever you're evaluating. It's just a constant, but it has a value. With me? So the weight in this case would be a over t tau rise, right? So we do all that, and we get C of n double prime equals a over capital T tau rise here. And then it's going to be first delta function turns on at 0. E to the 0 is 1. And it's going to be minus e to the minus jn omega naught tau rise. Minus e to the minus jn omega naught tau. Then plus e to the minus jn omega naught, and then it's going to be times tau plus tau rise. And that's it for C of n double prime. And I could stop there, but I'm not going to, because I don't know what that looks like. Do you remember what I did last time here?
You turned it into a sinc function?
I turned it into two sinc functions, but the way that I did it, and please remember this, is extract something that will make these things into sines first. Do you all remember that? Here's the trick. Just listen before I do too much. anytime I have 1 minus e to the minus j something, and I want to turn that into a trig function, it'll be either a sine or a cosine. What I do is factor out, all right, the value of that exponent divided by 2. So, I mean, it's really going to be e to the minus j and omega naught tau rise divided by 2. I factor that out, and I'm left with e to the plus j and omega naught tau rise over 2 minus e to the minus j and omega naught tau rise over 2. Do you all with me? Now that is a perfect sine, right? It's 2j times the sine of the argument times those exponentials. Do you remember this, class? I'll do it here just for completion. I'm going to have to erase this. And keep me straight on this. First we'll turn it into sines, then sinks. So what I end up doing is get my C of n here. This would be the double prime. Is going to be equal to A over capital T tau rise, right? And then over here I'm going to have, I factor out an e to the minus j and omega naught tau rise over 2. And I'm left with 1 minus e to the minus j and omega. Matter of fact, let me do one step before this. I didn't show you this. I should do this first. I can prove this if I take 1 minus e to the minus j and omega naught tau rise, and I multiply it by 1 minus e to the minus j and omega naught tau, I'll end up with this. Y'all see it? This times this is 1, right? This times 1 is here. This times this is here, right here. And then finally, this times this is this. Got me on this? So we do first inside, outside, last FOIL. We end up with that. That's the factor. Now, from these, I'm going to factor out the e to the minus j. I'm going to get them both here. E to the minus j and omega naught tau over 2. And also e to the minus j and omega naught tau over 2. Then I'm left with 2j squared times the sine of n omega naught tau rise over 2 times the sine of n omega naught tau over 2. And that's just noting e to the j theta plus e to the minus j theta is the definition of the sine over 2j of sine of theta. So here, my argument for sine theta was n omega naught tau rise over 2, right? Here and here, and I divide by 2j brings out a 2j upstairs squared. That's all well and good. That's C of n double prime. I'm sorry I left you there, if you remember, on Friday. All with me? So that's how we get to where we were. Now, I don't care about C of n double prime. I want the actual coefficient for the Fourier series that represents that pulse function, the rise time, fall time, and the duration tau, right? When I do that, I have to divide this by j and omega naught. And I'm going to put it right here squared. And that would be my C of n. So I'll divide it over here. You with me? The next part is just fitting form. I like to fit it in terms of a sinc function. Now that right there is probably a little daunting to some of you. All right? But here's the deal. If you look, if you want to get things in terms of a sinc function, what do I know? That the sinc of x, or sinc of x, is actually equal to the sine of x over x. You with me? So I've got the sine functions. I need this. What is that? It's the argument of the sine functions. I need that down here. So just watch this. If I take a look at this, I got a j squared right there, but what I can get, I'm going to leave the j. I'm just going to do this. You all see there's a j squared there? And y'all see there's a j squared here. Y'all agree they cancel? Good. So get rid of that. Next, I'm going to fit the form I want. I need this argument downstairs, n omega naught tau rise over 2. Y'all see how I have n omega naught squared here? So I just put n omega naught here, and I put n omega naught here. That's the same thing as n omega naught squared, isn't it, class? Right? Now, what do I need? I need a tau rise downstairs. Right? I got a tau rise right here, don't I? So I put a tau rise over there. I also need a tau. I don't have a tau, so I multiply top and bottom by tau. You all see what I'm up to? All right, it's all going to fit well. Now you'll notice I have a 2 squared. If I multiply top and bottom by 1 over 2 squared, I divide this by 2 and this by 2, don't I? Y'all with me? Well, what do you think I have right there?
Sync.
Those don't look like 2 sinc functions. I don't know what does. Isn't that right? Different arguments, but 2 sinc functions. So finally what I can do is say C of n is equal to A. That's just the height of that pulse, right? It was at A, it goes down. A, and it's times tau over the period. And it's times this exponential. This is a phase term I could care less about. E to the minus j n omega naught. And it's really going to be 1 over 2. But it's going to be tau plus tau rise is the coefficient, isn't it? And then it's times the sinc functions. Times the sinc. And this would be n omega naught tau rise over 2. These are sinc functions times the sinc function of n omega naught tau over 2. Are you with me? What C of n is that? That's the C of n for the actual Fourier series. Back when I was putting it up here, I said x of t was equal to that summation from n equals minus infinity to infinity, right? Of C of n e to the j n omega naught t. Here, omega naught has to do with the repetitive period, right? T. So 2 pi, or you could say f naught is 1 over the period. Omega naught would be 2 pi over t. You with me? Okay, now that's still periodic and it's still a little abstract. This at least is getting to something you understand, because you know the magnitude of sinc waveform does what? It kind of looks like a sine or cosine wave divided by the argument x, like cosine of x over x. If you take a look at it, it goes, it keeps going down, right? Keep watching, this is good, and this is so important. When I teach EMC and radar, I go through this in detail, how it applies to systems, and how it can affect systems, and how to easily analyze this. So that's what it is for a waveform of a certain rise time, certain fall time, or excuse me, certain rise time, certain duty cycle. Let me ask you this. You all see this tau over t? Remember what that stood for. If this is t, our waveform went up to A. This is our original x of t here. Stayed there. This would be t rise. Then came down. The width here is tau. This would be, right here would be tau. This would be tau plus tau rise. And it repeats itself, right? So that x of t would have this coefficient right there. And you'll notice the duty cycle, or right here, this duty cycle is tau over cap t, right? It's just the duty cycle. If you look at this is nothing but a phase term, right? And this is the thing that gives it the unique signature. Now, I'm not done yet, but I want to get through that part. Now, hear me on this next part. Not quite done with how we do analysis. So the next thing I'm going to do is take this series right here and turn it into something very useful for analyzing circuits. I'm going to turn it into a cosine series, not an exponential series. Some of you probably remember this. So I take that x of t. Remember, the summation goes from minus infinity to infinity. So I say x of t is going to be equal to the summation here from n equals minus infinity to minus 1 of c of n e to the j n omega naught t plus the summation from n equals 1 to infinity of c of n e to the j n omega naught t. And then it's plus c0. And some of you remember that c0 was equal to 1 over the period, the integral from t over 2 to, or minus t over 2 to t over 2 of just x of t dt. What is another word for c0?
Average value?
It's just the average value. And you could do it this way. You could say it's really the average value of x. All right? That's all it is. So for this one, what would the average value be? Well, you would take what? The width of from here to here is tau, but what would you really do? You could say it's going to be this length of time, tau, right? Minus t rise times a, plus, and then, since these are identical triangles, just take one and multiply by 2, plus tau rise times a, right? And that would be the area. Y'all follow me? That's all it is. All right? That would be x0. Now, why did I get, anybody want to take a gander why I did this right here? Took a shot at? Some bright people in here. Well, let me show you something. Now listen. Let's see how C of n, I don't have it up here, but C of n's definition, I'll put it right here. The definition says that equals 1 over t, the integral from minus t over 2 to t over 2, of x of t e to the j minus j n omega naught t dt. With me? Now, hear me. All right? If I take the conjugate of that, that's the symbol for conjugation. The only thing that happens is that becomes plus. You all see that? With me? Now I can go ahead and say, if I take a look at this series, x of t, I can actually say it's equal to a summation of c of n conjugate right here times e to the minus j, or excuse me, e to the minus j n omega naught t. What I'm going to do now is make n positive. Follow me. If n goes from minus 1 to minus infinity, the order makes no difference. If I made this positive infinity, positive 1, I would make the coefficient on j negative. You with me on this? That's conjugating it, and I'd have to conjugate c of n. All right? That's the reason. Because if you conjugate, instead of summing over a negative values, you sum over positive values, and that's it. So now I'm going to sum here, right? Plus, and then I'm going to get this, another summation equals 1 to infinity of c of n just by itself times e to the j n omega naught t plus c0. And now you can see, since the summation is over the same range, right? And the argument is here, when I have c of n conjugated here, I'll tell you what I can do. Y'all see if I just focus on the exponentials. If I have e to the jn omega naught plus e to the minus jn omega naught, isn't that the 2 cosine of that argument? How many see that? Right? If you don't, let me just put it up here. If you talk about a cosine of x, that's equal to e to the jx plus e to the minus jx. That's all it is. Whatever the argument x is. So when I do this, I've got this and this. One other thing, c of n actually, well, let me do it this way. C of n can be rendered as magnitude of c of n e to the j angle of c of n, can it? Do you all agree with that? It's a complex number, Jenna. It's got a magnitude and an angle, right? Now, what does that really mean? Well, when I conjugate it, the only thing I do is change the angle there, don't I? Y'all see that? This J would go from a plus to a minus. So I'm going to go ahead and put that in here so you can see this, and I'll get to the point in a second. So this is really going to be magnitude of C of n. Since it's conjugated, it would be minus, so I can put it minus Jn omega naught t plus the angle of C of n here. And then I can do the same here by making this magnitude and making this argument n omega naught plus the angle of C of n. Now, if you had me for signals and systems, you remember that. I'm going to give you the summary shot of this in a second once I'm done with everything. I just want to see you to see the proof. You with me, class? Okay? Everybody? Now, at this point, you all see how these arguments here and here are identical, so we can turn it into a cosine series. This is the whole point. And now we take x of t, and we say it's equal to, and I'll put C0 first, the average value plus the summation here of, and it'll be 2 times the magnitude of C of n times a cosine of n omega naught t plus the phase angle of C of n. And here n goes from 1 to infinity. Now I gave you the value of C of n right here. But I want you to see the entirety of what's going on. We're still not done, but you have to understand what I'm trying to get at is the frequency response of systems. And you can see that this thing has unique frequencies. When n is equal to 1, that's called the fundamental. That's when this cosine waveform's oscillating at just omega naught. When n is 2, it's the second harmonic, right? When n is 3, it's the third harmonic. Do you all remember this from COM and your signals and systems courses, right? So this is important. Each frequency has a different weight. And the weight is given by C of n. Do you all see that? So if I wanted to know if I'm putting this thing, this functional form, by the way, can I erase that now? Because I need a board here. Do you need another picture? Just yell at me if you need me to stop or anything. Y'all good with this? Okay. So now, here's the deal. Remember that right there. It's in terms of cosines. So here's the thing. Now if we have a circuit, we have a system with an h function. What is h always?
Transfer function.
Yeah, it's h of omega is really equal to v out of omega over v in of omega. Frankly, it's the output over input. Whether it's v or I, it doesn't matter, right? Just relates, and that's a transfer function. So if I say I'm putting this square wave right here, that's my x of t, I'm going to drive something with a known transfer function, and I want to find out what the output is right here. I can just call that y of t. Here's how I can do it. I can take that Fourier series x of t, and I can convolve it with the time domain version of h, right? I can get the impulse response. Or better yet, what I can do, and this is the nice thing, y of t here will be this. If I just take let's do it this way. Suppose my signal coming in here is just x of t is equal to 5 times cosine of omega naught t plus 10 degrees. All right, volts going in. How do I get the output? Anyway, are you going to do it in time domain? No, we would make a phasor out of it. It's at a constant frequency, right? We would say this is a phasor of magnitude 5. That would be x in a sense of omega. It's a phasor, and it would be at an angle of 10 degrees. Now we know the frequency because omega naught, if it's given, would tell us, right? Now we come out here and we say, well, y of t, forget y of t, y phasor, right? Omega, it's not even a function of omega technically right there, would just be the input value, 5 at an angle of 10 degrees, times the transfer function evaluated at omega naught. You with me? Right? Now you got an output. But in order to get what? To get the time domain form, do you remember how to do this? Anybody? Suppose my output, just for kicks, is say 12 at an angle of 40 degrees. How do I get the time domain form of that? Do you remember? Well, there's a technical way. That's a phasor, right? So remember, if I want y of t, please remember this. That's the real part of, and then you're going to have to remultiply it by j omega naught t times the phasor form. In this case, times y phasor of omega. So when you do this, now remember, when I put in this, I get 12 at an angle of 40 degrees, right? That can be rendered as 12e to the j 40 degrees. Do you all agree with that? You all with me with exponential notation? E to the j 40 degrees times the weight 12. So that means the output would be the real part of e to the j omega t times that. Anybody want to take a guess what that is? It's a cosine, right? Remember, if you take the real part of something, of e to the j omega t, you get the cosine. If you take the imaginary part, you get the sine. Don't you, class? Do y'all remember that? All right, so what you end up getting is simply the cosine of omega naught t plus the phase angle, the original phase angle. Right? Well, actually, if I'm saying it's just plus 40 degrees. And technically, this isn't correct because this should be in radians. This unit, omega naught, almost always is in radians per second. So times t would be radians. So you would need to change 40 degrees into radians. Y'all follow me on that, class? Technically. This goes on for one term. With our Fourier series, I have an infinite series of terms, don't I? But what I can do is take in, now just listen to this, I'm trying to make this point clearly. I can go ahead, if this is the weight, and that's the frequency for the first harmonic, I would put a 2 omega naught in here, right? And then whatever the second harmonic's value would be there, and then I would take that value in the phasor domain, multiply it by the transfer function evaluated at the second harmonic, right? And then do the real part of that, times e to the j omega t to get the time domain. Let me cut through the crap and just get to the bottom line. If you have a system with a periodic input and you know the Fourier series, cosine series of it, then you can do this. Just write down and underscore. So if I have a system and I have the Fourier series of it, I have plus or minus x of t here, and it's going into some filter, h of omega, input output, and now I want this output, y of t. What I can do is take the original Fourier series, so in this case it's C0, but I have to multiply it by the transfer function evaluated at 0, plus, then it's going to be that summation from n equals 1 to infinity. This is going to be the cosine series of 2 times magnitude of c of n. Remember, each value of n's got a different coefficient here. Then it's going to be times the magnitude of h of n omega naught. So now you need to evaluate the transfer function at each harmonic. Then it's times the cosine. This is how phasor analysis works. If you want a continuous time, cosine of n omega naught t plus the phase angle of c of n plus the phase angle of h of n omega naught. All right. Does anybody remember that from signals and systems? If you had me, who else had me for signals and systems? Do you remember? Okay, these two do. This is so important because what it does is says we've got any periodic signal, anything at all. You get the Fourier coefficients for it. If you want input-output, there it is. If I wanted to know the output right there, the fourth harmonic, I would just plug in n equal 4. And I've got it, and this is time domain. If I just want the magnitude, the only thing I need is this, right? Because that cosine waveform goes away when we worry about magnitude, doesn't it? We just worry about that. You all see what's going on here? Now, some of you are thinking this is a far cry from EMEG right now. Well, this is the signal you're analyzing. Now let me show you the frequency domain, why I did that, but I'm going to make it easy. I'm going to erase that. So I'm going to try to make it easy. Try to make it apparent to you. By the way, this is stuff I'm very interested in because there's so many things that this impacts. If you have a good understanding of this, you'll be able to analyze so many different systems. You can do radar work, you can do EMC work, you can do high frequency device design. All right, now, what I was showing you is what's going on with C of N right here. Just watch this. If you actually look at a plot of this, and let's plot the logarithmic frequency here, so it'll be like then. And you get the idea. You're going to have logarithms. This could be 1, 10, 100. It's the log on this. And if I take the 20 times the log right here of the magnitude of 2 times magnitude of C of N, and the reason is for the cosine series, I erased it. For the cosine series, the coefficient is 2 times C of N for x of t, right? So if we look at this, this would be the Fourier spectrum of the signal x as a function of omega. Actually, I'm going to make it a function of f, but let me go here and do this. Let me show you a trick. I want to make this versus f, so it'll be really clear and apparent to you. Now please watch. Are you with me so far? You're hanging on. I know a lot of this is coming at you kind of hard if you haven't seen it the first time, but Fourier analysis is something you saw. Now you're seeing an application of why it's important. Because you can get phasor terms that you can stick into a circuit and get the output. Now I have this. Well, omega is 2 pi f. Do you agree with that? So if I put down 2 pi f here, the 2 would go away, and I would have pi, right, times f naught. Here, I would have pi times f naught as well. You all follow me on that? I'm just replacing omega naught by 2 pi f. And f naught is 1 over a period. Agreed? All right. Now if I look at this sync waveform, and I think to myself what it looks like, well, I better do it over here. Do you remember what the sine of x over x looks like, which is the sync waveform? It does what? If we just talk about this as magnitude of the sync of x, what do we see? Something like that, right? Y'all remember this? This is so important. So what's that point? Well, that's the first zero of the sine after x equals 0. When is sine 0 next? At 0 and at pi, right? So this would be, right here, pi, correct? Where's this? 2 pi. As a matter of fact, one thing you might want to put down here, this will be exactly, well, almost, minus 13.45 dB lower than this point if it was in log. Yeah?
I thought the sync function went underneath the x-axis.
Well, this is magnitude. I just want to show you magnitudes because I can do that, but I'm going to level with you. We care about the magnitude. That's what we really care about. All right, that's what a sync function does like. The key is this. So if we're plotting this versus frequency, now just get this down. What you'd start off with would just be 20 times the log of 2 magnitude of C of N. That's all you'd have for quite a while. That's when x values, the arguments of those sync functions is real low. You got about 1 there. Follow me? All right. So when these functions, both of these two have arguments that are small. That's at omega 0, stuff like that. The only thing you get is this term right here. When we take the log of this, we get 2 times, or the 20 times the log of 2 times a tau over t. And it stays there. That's all it is. So I can put this as 2 times A times quantity tau over T right here. It's going to stay there. And the first frequency it's going to start falling at is where this one right here has a value of pi. What do you notice? Matter of fact, let's do it this way. And I'm trying to fit this all into one lecture. Instead of using NF naught, just put F there and we'll get the envelope. That's the critical thing. So instead of NF naught, because that's just at every given harmonic, we can just call this times F here. And you can call this times F. It's really going to be F pi and then tau. Now, hear me. You with me on this? I'm going to just get the envelope of C of n. That's all it is. It's not actually going to be the value. But if I look at this envelope, one thing I notice is between these two, I have to set them both equal to pi and see where it goes, where that's going to be, where it occurs. So if I set this one equal to pi, I find that F is 1 over tau rise. So when I set this one equal to pi, pi's go away, I get F tau equal 1. I get F is 1 over tau. Now, because tau is longer than the rise time, always, it will be your first frequency. So right here, you'll get 1 over tau versus F, and this waveform will start falling at minus 20 dB per decade. Please just understand this is an approximation of the magnitude of those coefficients in the cosine waveform. It'll stick there at minus 20 dB until I hit 1 over tau rise, and then it will start going down to minus 40 dB. I got 1 minute left, and I'm trying. Now just listen. Some of you are saying, well, how'd you get that, Dr. McGinty? Just take a magnitude of this, just for now, all right? And multiply it by 2. That gets rid of this completely, right? Now, a sinc function, as if you actually look at this, what this looks like is just the sine function divided by a 1 over x. With me? Are you all with me? So what happens really when this sine function here turns on, this one's the first, then this thing starts falling as 1 over x. Well, if I take 20 times the log of 1 over x, I get minus 20x, right? And it starts falling down at 20 dB per decade right here. That's when the frequency is 1 over tau. Are you with me? And then it keeps going down at that rate until you hit a frequency of 1 over tau rise. Now, some books are going to show you, well, they're going to show you different, they're going to define the sinc function as something different. Actually, let me do it this way. Since that is, this is over 2, pardon me. No, actually that's right. But this should actually be pi here. It's my bad on this one.
It was 2 pi and then you canceled out the 2's.
Yeah, it's 2 pi tau rise, and that would be pi equals f pi tau rise. Let me check on that. I think it's the definition of the sinc function that's different, but when this is done, hold on for 1 second. There will be a pi in here, and I got to check out one thing. There should be a pi there, and I'm going to put this down and make it real clear for you in your notes. Now, here's what we're going to do. I'm going to show you how to use this stuff to estimate. If you look at this, this is nothing like the bandwidth approximation in Dr. Wimmer's book. This is a much more detailed approach. Wimmer's book basically says, well, the bandwidth is about 1 over tau rise. Right? That is absolutely true of a general way of doing this. If we needed an amplifier to amplify that signal going in, you want to have an amplifier that's at least out to here, all right, frequency-wise. And you need a linear amplification out to that frequency. However, you can see that it is it's anything but that simple, the way this thing's going. I'll give you some more information, some problems, and on Wednesday, this thing should come together. The problems will help you see it, and I'll put in the notes the exact formulas, okay? Hope this helps somewhat. Sorry, I ran out of time.